In this video, I will talk about principal component analysis and factor analysis. Click on the link below the video to go to the website and find more information on this topic. In this presentation, I will first go over a principal component analysis, or PCA, and factor analysis overview. Then I will talk about the PCA methodology. I will talk about component factor retention, or component/factor rotation, and this would be the orthogonal or oblique rotations. And then I will talk about when to use principal component analysis, and I will conclude with exploratory factor analysis. So what are principal component analysis and factor analysis? They are data reduction methods used to re-express multivariate data with fewer dimensions. So what we mean here is that we have a lot of variables in your data set, and you wonder if all of them should be used in an analysis or some of them might be redundant, and you can express all of those variables with fewer factors or components. So the goal of these methods is to reorient the data so that many original variables can be summarized with very few factors or components that capture maximum possible information or the variation in the data from the original variables. So the PCA analysis is also useful for identifying patterns of associations across variables. So these two methods are very similar, principal component analysis and factor analysis, and are often used interchangeably, but they do have a little bit of difference between them, and that's that a factor analysis assumes the existence of a few common factors that drive the variation in the data. We just don't know what they are or how to measure them really well, but we know that there are a few common factors. Whereas principal component analysis does not make such an assumption. You just have data and you're interested in the most efficient way to represent this data. Okay, so here's a little bit more about the PCA methodology. So the goal is to find components, and we have here Z equals from Z1 to ZP. These are P number of components, which are a linear combination of the original variables X equals X1 to XP that achieve the maximum variance. So if we have the number of original variables equal to P, those variables can be represented as components, which are in the same number of components, but that are just reoriented a little bit differently. So how are they reoriented? Well, the first component, Z1, is given by the linear combination of the original variables and accounts for the maximum possible variance. So we're interested, given all these X variables, can we just come up with one component that captures as much as possible from the variation in the data, like 50% or something, with just one variable or component? So the second component would capture most information that's not in the first component, and it's also desirable that it is uncorrelated with the first component. So this will be the requirement for the second, third, and so on components. So PCA seeks to maximize the variance, and so it is sensitive to the scale difference in variables. So for example, if you have a survey that has attitude questions from 1 to 7 rank things, then you can use a covariance matrix. But if you have variables, one of them is measured in dollars, one of them is measured in people, one of numbers, one of them is measured in proportions or something like that, then it's better to use with correlations in your data because of scale issues rather than the covariance of original variables. So going back, PCA maximizes the variance, such as Z equals X U, and we have that U prime U equals 1. So again, we want to find those components that are linear combination of the original variables that summarize the data in the most efficient way. And the solution would be obtained by what we call eigenvalue decomposition of the correlation matrix of the x variables by finding principal x's of the shape formed by the scatter plot of the data. And so these eigenvectors would represent the direction of one of these principal axes. So what we mean here is, suppose you have two original variables, x1 and x2, and then the data is like a scatter plot. Can we find a different dimension, maybe like going like that in the middle, that would summarize this variation in the best possible way? And then maybe a second one, uncorrelated dimension, that would summarize the next possible variation in the data. So this is what we're trying to do here. So we would be solving the equation r minus lambda I for the identity matrix times u equals 0. And this r would be the sample correlation matrix of the original variables x. This lambda right here is called the eigenvalue, and u would be the eigenvector. And so these lambdas are the variances associated with the components or the factors. And the diagonal covariance matrix of the components, we would denote that with a d, a diagonal of lambda, and these would be reported in the results as the eigenvalues. The proportion of the variance in each original variable xi that is accounted by the first c factors would be given by the sum of the squared factor loadings. So the summation from 1 to the c number of factors would be equal to f squared of ik. And so when we have that all of the components are retained, so c, the number of factors, equal p, the number of original variables, then we would have that the summation of the squared factor loadings would be equal to 1, or all the variation in the data are explained. And that intuitively makes sense, because if you have 13 variables, you can summarize that absolutely all of the variation in this data with 13 components. So that would be always a true statement here. So the factor loadings are the correlations between the original variables x and the components factor z, which would be the correlation of x and z, and that is also u times d to 1/2, and we will actually look at these in the example section in the next video. So now, because the factor loadings matrix shows the correlation between the factors and the original variables, we would have that typically those factors are named after the set of variables they're mostly correlated with. So for example, if you're doing a survey and you kind of know which factors are important, you could have several questions representing those factors, and then your analysis would again show you which questions really load on which factors, would confirm that. And another thing that we're going to do here is that the components can also be rotated to simplify the structure of the loadings matrix, and also to facilitate the interpretation of the results. Okay, so next, what is important is the topic of factor retention or component retention. So since PCA and factor analysis are data reduction methods, there's a need to retain an appropriate number of factors based on the trade-off between simplicity, so we want to retain as few factors as possible, and completeness, we want to explain most of the variation in the data. So how many should we retain? So one rule is the Kaiser rule, which recommends that you retain only factors with eigenvalues lambda exceeding unity, which means that any retained factor z would account for at least as much variation as any of the original variables, and it makes sense. This is a tool called a scree plot, where we can examine the eigenvalues after PCA. and see how many to retain. And so in this example, we have the first principal component has an eigenvalue of 3 point something, then 2 point something, about 2, and then just above 1, and so on. And this is the 1. And the Kaiser rule says that anything above 1 should be retained. So we have 1, 2, 3, 4, 5, according to this rule, should be retained. Here in this different example, we have one eigenvalue that's about 4 point something, and one that's very close to 1. And so according to this Kaiser rule, again, here we should retain 2. Now, in practice, we would need to examine the scree plot to determine if there is a break in the plot with the remaining factors explaining considerably less variation, or kind of like an elbow, as they call it. So in this case, I mean, look at this one, there's like a significant break here between the third and the fourth and the fifth, and these are getting close to 1. So in this case, you may also use like the first 3 factors, or try both ways, use 5 and use 3 and see which one is better. In this case, I mean, this factor, you know, this eigenvalue is above 1, but just barely so. So you may just want to use one component that expresses all of these original variables. Okay, another topic to consider is factor rotation. And the factor loadings matrix is usually rotated or reoriented in order to make most factor loadings or any specific factor small, while only the few of them being large in absolute value. So what we're doing with this factor rotation is you're trying to have as few as possible of the original variables loading on a factor or a component, but with highest possible values. So we want highest possible correlations on fewest possible factors. That's the goal here. And this simple structure would allow these factors to be easily interpreted as clusters of variables that are highly correlated with the factor. And again, we want to be able to define clusters of variables that to large extent define only one factor, because if you have original variables that load on several factors, then the interpretation gets a little bit harder. So there are 2 types of rotations typically used. One of them is called orthogonal and one of them is called oblique. With the orthogonal rotation, it preserves the perpendicularity of axes. What it means is that these rotated components or factors remain uncorrelated with each other. And some people think that's a desirable property. And the one that we would consider is the Varimax rotation, which preserves the structure by focusing on the columns on the factor loading matrix. And it's aiming, so the Kaiser's Varimax rotation is aiming to maximize the squared loadings variance across the variables summed over all the factors. Whereas the Quadramax rotation preserves that structure by focusing on the rows of the factor loading matrix. So on the other hand, with an oblique rotation, that one allows for correlation between the rotated factors, and the purpose is to align those factor axes as close as possible to the groups of the original variables, and we want to facilitate the interpretation of the results. So some authors think that that's actually a better approach, since a lot of the variables or factors in real life are correlated amongst each other. So that would represent the natural phenomenon better. And a rotation that we will use here is called a Promax rotation, and that's an oblique rotation. So when is it appropriate to use principal component analysis? It should be undertaken in cases when there's sufficient correlation among the original variables to warrant this factor or component representation. So if you have data that is mostly uncorrelated with each other, then why should we try to summarize it using common, factors or just using fewer components? But if there is very high degree of correlation among your variables, then is a good example of when to use these data reduction methods. So the Kaiser-Meyer-Olkin measure, or KMO measure of sampling adequacy, would take values between 0 and 1, and if you have very small values, indicating that the overall variables have little in common to warrant principal component analysis, whereas values above 0.1 are considered satisfactory for principal component analysis. And that's one measure that we will use. Another one is the Bartlett's sphericity test, which examines whether this correlation matrix should be factored, which means are the data dependent or independent. And that is a chi-square test with a test statistic that is a function of the determinant of the correlation matrix of the variables. Now, a little bit about factor analysis, in particular exploratory factor analysis, and we would think about the common factor model. And there, under this model, the observed variance in each measure is attributable to a relatively small number of common factors and a single specific factor, unrelated to other factors in the model. So we would have here xi, so this is an original variable that we have in the data set, would be equal to lambda I1, xi1, and so on, plus delta I. So these would be the common factors that we would uncover during the analysis, xi1, xi2, and so on to xi-c, and they would be representing the original variable. And this specific factor here, delta, could be thought of as the error term. So again, these are the common factors, and they're common because they might also appear for the other variables, and this is the error term that is specific to this variable. Now, factor analysis would be appropriate when there is a latent trait or unobservable characteristic. So if we know that there's some kind of factors that explain the data, but we can't measure them very well or observe them very well, that's a good scenario to apply the factor analysis. And one of the useful things of factor analysis is that these factor scores can be obtained from the analysis of dependence. So instead of like using the original variables, you could now use the factor scores that represent the data. And factor analysis is typically used with survey questions about attitude, and the goal here is to identify common factors capturing the variance from these questions, and which can also be used as factor scores. Now, several assumptions to determine a solution of a common factor model, and basically that everything is uncorrelated with everything. So the common factors are uncorrelated with each other, the specific factors are uncorrelated with each other, and the common factor and the specific factors are uncorrelated with each other. This is an assumption we're making. And now we'll talk about the communality. The communality is the proportion of variance in the X that's attributable to the common factors. So this is the proportion of variance in X attributable to the common factors, but it's also equal to 1 minus theta squared II, and this theta squared is the variance of delta I. These are the so to speak, these are the error term that I talked about on the previous slide. So this one represents a factor uniqueness. So in some of the examples we're going to see that is the factor uniqueness. 1 minus this is the communality. So basically we either have communality, which means there's part of the variation that is attributable to a factor across all the variables, or there is just factor uniqueness that just belongs that is just based on a particular variable that's not accounted by the factors. Okay, so the solution to the common factor model is determined by reorienting the first factor so that it captures the greatest possible variance, and then the second factor so that it captures the greatest possible variance that's not already accounted for, and it's uncorrelated with the first factor. So this is exactly the same as we had with principal component analysis. So now the correlation between the original x variables and these psi factors are called the factor loadings, lambda, and once we have that, we can represent the factor scores, which are the positions of the observations in the common factor space, or the factor scores coefficient b would be equal to r to the minus 1. This r is the correlation matrix of the original variables, and we have this lambda, which is the factor loadings. So we basically could obtain these factor score coefficients. So now once we have the factor score coefficients, we could calculate the factor scores as psi equals xs times beta, where beta is this factor scores coefficient, and then we have the original variables here. So these factor scores are included in the data, and they could be used instead of the original variables. Okay, so this was a very quick introduction of principal component analysis and factor analysis. Now join me in watching the next video on principal component analysis example.